Okay, I think we can start with you, Mike. When you want, you can share your. Maybe I have to. Mm,
If I
okay.
can
I think now you can. Let's try.
Mhm.
Perfect.
Oh.
Are you sharing that?
Okay.
Also just
Do you see my full screen now? No. Do you see the presentation now in full screen or not?
No, it's PowerPoint mode.
Okay, sorry.
It's always challenging with that screen.
Yeah, how
you should just restart the show.
sorry, I think I will need a few minutes to set it up properly.
No, I think you can just restart the sharing and select the other screen.
Yeah, but then you still can't see
No,
it.
that should be fine.
Okay. And then I reshare.
Okay, now it's going.
Oh,
Was good before.
it's good now?
Yes.
Okay, perfect. Okay, so I'll start. Yeah, I just put up the slides from the last meeting. I'm still working on the same topic, and today I will show some more models that I presented last time. So last time I mainly presented my reference model, which is this one. This is not the attached slab that went wrong. Left we have an attached slab model. In the middle, I'm showing the reference model that I presented at the thread meeting 2 weeks ago. And then on the right is a different geometrical variation that I'm testing where we don't have where the two plates are not overlapping and there's a very shallow break off. And today I will focus a bit on that model as recently I've been testing with different Moho geometries and I found out that the model results at the surface are very sensitive to the exact geometry that I put for the Moho. And by tuning this geometry, we can obtain a similar result at the surface as with the model where the breakoff is deeper. So this is the Moho depth data that I'm using from receiver functions. And as you can see, in the area where the plates are overlapping, it is not so clear what the exact geometry should be of the plates. The authors had suggested a symmetrical geometry, a bit like this. However, I think we can also put some other interpretations, such as this one, or where the left one goes a bit deeper, or maybe even shallower. And the exact depth of the overriding plate is quite important for the viscosity of that layer and therefore for the model results, which I will show later, because the interpretation that you choose can result in a 20-kilometer difference of the depth of the lower crust. So this is actually quite important. So I drew some different Moho geometries. This is the one I was using at first. Then I tried geometries where the plates are a bit more, where the lower crust of the terranean, that is this left one, is a bit higher, and therefore it will be less ductile, so stiffer. And then I run a few variations on these models, and on the right are a bit more, are even more extreme cases where it's even shallower. And then I will show you the results. I'm sure it will be a lot of figures on one slide, but I will talk you through it. So here I'm showing 4 models. Don't pay attention to the color code, it's the same in every model. But so the only difference in these models is the geometry of the Moho and how the lower crusts are overlapping. And then I'm showing the deviatory normal stress, where green is extension and blue compression. And as you can see, with the 2 models on the left, we mainly create extension near the surface, whereas with the Moho geometry on the right, there's a lot more compression in the upper near the surface. So quite different results, and that is all related to the viscosity of the lower crust. Here I'm showing the viscosity, and as you can see here, where the lower crust is a bit shallower, there's more pink, which means that it is stiffer. Whereas if we put the lower crust a bit deeper, we create this ductile gateway, I would call it, that allows for the mantle flow. This is the vertical velocity, so blue goes upward, and this mantle flow that we have in this window can transfer all the way to the surface. Whereas if the lower crust is a bit more shallower and stiffer, it blocks the mantle flow and it doesn't transfer all the mantle flow to the surface. And with this model on the left, there is barely any mantle flow because the lower crust is blocking this. So small changes in Moho geometry have a big impact on my model results. And so here I'm showing the horizontal surface velocities, where in green there are the observations, and in blue and black the different models. And these are from all the different models I just showed. And as you can see, some have a quite good fit with the observations, whereas others barely generate surface velocities. And if I then take the model that best matches the observations and compare it with the Moho where the plates are more overlapping, that I chose as my reference model. If we then compare these two, actually at the surface, I can obtain very similar results. So an area of extension with some compression in the Adriatic Sea, and the surface velocities are also very similar actually, whereas the mechanisms that drive this are quite different. On the left, the main driver would be mantle upward flow transfer to the surface, and on the right, the main driver is the outward flow of the upper crust. So yeah, I'm still running a bit more models to see if I can discriminate further between these scenarios. But so far it seems challenging to be able to distinguish between these two models. And then I also have some more exciting news. And that is that I started collaborating with Alexander, and we managed to load my Central Apennine setup into his STM rate saving friction model. And so with this model, we will be able to fully resolve and simulate earthquakes. And yeah, we already managed to load in the setup, and now we just have to tweak the parameters and solve some technical issues. But yeah, I think that's an exciting outlook. And I think Alexander will probably later show some more results.
Hopefully.
And that's it.
Thanks a lot, Mike. Any question from the others? Seems no questions. Okay, we are curious to see.
So maybe I have one then.
Yeah, sure.
Because I didn't see the last result yet of Mike.
I saw the results this morning, and these are new again. So
So could you maybe explain a bit better the two figures and what's
Which two figures?
yeah, this one, yeah. This
this one. Okay, so I also saw these this morning.
I created 2 hours ago,
So it's very new. But this is the strain that has built up in the model since the transitioning to the rate and state friction in the model, and so loading of the short term.
this is
okay. So the starting point,
Transition.
Yeah.
Okay.
the starting point at you start at year 0. It's the output of your previous model, right?
No, not the output, but the setup.
The setup, but the final step of, I mean, for instance, the stress,
No.
the stress field. How is the stress field is derived from the result of your STM model?
No, only the initial setup is taken from the. We use the same initial setup and then we rerun the long-term parts, and then it transitions to shorter time steps.
So you start at T0 of your old models.
Yes.
But from which time of your old model?
T0. First
At T0 also of the old model. Okay. Okay. But okay. And why not the last step? Why not starting from the?
Because we can compute everything in this model, so that's
Okay.
we don't have to take output from the other model.
Okay.
the initial phase is basically the same as in the other model where the faults are initially loaded. So it's basically doing the same thing initially, and this bottom figure is from this. So this is very similar to what would happen in the long term of the old model. It's not exactly the same because some material parameters are not yet right, but it's basically the same of all faults being active in some way, but there are no distinct events. And then at the top, there is one distinct event that has happened.
Yeah, so this also gives you time to calculate state variables and anything, because also if you would start at the end of the previous model, you would have to go again in a re-equilibration phase because you're using rate and state friction rather than a strongly slip rate dependent friction. So if you have to go through a transition phase anyway, you might just start at what we directly have from the observations.
Okay, thanks.
And how does this this faulting pattern that you have below compare to the active fault area in the Central Apennines?
Well, I didn't compare this one, but the faults that are activated are very similar as in my own models. It's
Okay,
you
good.
can.
The cohesion isn't the same. There's
Yeah.
still an error here in the plastic parameters that also affects the long term. So
And in this figure, you can also see I drew the faults, I think, up to 10 kilometers roughly, and then below the model, just made faults where there should be faults according to stress and strength. And you see that there it's a bit more dispersed, less localized.
Yeah. Cool.
And Bruno, what do you think about this this geometry, for instance? Does it look not unrealistic at least, or realistic in terms of the depth?
I
Take
can
your
say
glasses.
not totally, but it's could be a starting. It's
Well, it's better than what we have from the observations, right? If you look at the
Yeah, sure.
observations, we don't know what to do below 10 kilometers.
Yeah, sure.
So Mike has been trying to work on that in the last few weeks as well with some structural geologists here. But yeah, we just don't know. And that's a big problem in any of the other models if we are defining faults, right? We don't know what they do below 10 kilometers of depth.
Yeah, sure.
We don't know the MOHO, that it becomes complicated.
No, I agree.
This also changes in the short term because once you have actual earthquakes, your deformation will localize in a different way than it does in the long term. So
yeah, and that comparison is interesting as well, right? Because it also holds for the comparison with, for example, geodetic observations. So that's what Mike will still work on. Thank you, Mike.
Thank you, Mike. We can move to Aurora.
Sure. I'll share the screen. Can you see it in presentation mode?
Yeah.
Okay. So yes, most of the things that I'll show you today, maybe you already saw them last month at the TRED annual meeting, but yeah, maybe I'll go more into detail today. So first, a very quick recap. I might have said a few times that we are interested in to get to know a seismic processes better because it's clear that perturbing the stress state in the subsurface, they can control, trigger, or prevent seismicity. So understanding a seismic processes means also understanding earthquake physics itself. And on the other side, if we know specific pattern, we can somehow forecast seismic events behavior in time and space. And I guess this would help improving or updating current earthquake hazard models. So at the moment, my current focus is characterizing aseismic slip events, which are one of the possible seismic processes which can trigger or suppress seismicity. Of course, we will consider other mechanisms like pore pressure diffusion or the poroelastic effect and so on. And we will consider the fact that all these mechanisms may interact. And of course, the final goal would be understanding if we are capable of quantifying the seismic signatures that might be related to the potentially a seismic driver. So the fact is that at the natural scale is quite complicated to go back to the potential aseismic driver because the only thing that we see clearly is seismicity itself. We also have, of course, large scale surface deformation data in some cases, but in any case, all these aseismic processes are inferred, and they are inferred from seismicity because it seems that some signatures related to different aseismic processes exist in seismicity, and some of them are, for example, the different spatial decay of the density of seismic events from injection points or from modeled seismic slip front. We have seen that forefront and backfront in seismicity exist, and another potential signature could be the absence or delay in time of a clear main shock. Anyway, all these signatures are used to infer the aseismic driver, but the key is that understanding how seismicity is related to this driver is quite complex if we do not directly measure these aseismic mechanism. And this is where Bedretto Lab and the FEAR project entered the scenario, because in Bedretto Lab we have this quite unique opportunity to measure from up to close fold deformation. It might be slow or fast. We can measure pressure field, we can measure seismicity, because we have an extremely extensive 3D monitoring array. And then let's say the main goal of the FEAR project is to study the seismic and hydromechanical response of a fault zone to fluid injection. And for this purpose, we have installed sensors both on and off the fault or rupture area. And in the end, we aim to study how ruptures nucleate, evolve, and also how seismicity behaves in terms of spatiotemporal patterns related to the different fluid simulations. Bedretto Lab is placed into a tunnel, so it's the perfect place because we can almost study earthquakes at the natural scales, but not exactly. We have 1,000 meters of granite overburden. And so, okay, so FEAR 1, can you see my pointer? Okay, I assume you can. Okay,
Yes.
thanks. So the FEAR 1 experiment has been completed in December last year, and it took place in what we call the earthquake physics testbed. So here you have a scheme of the experimental setup. The main goal of this specific experiment was to characterize the hydromechanical response of the target fault zone that is identified by these two surfaces in gray and light blue to fluid simulation. And then the goal of FEAR 2 will be make this fault move seismically and host nearly magnitude 1 event, but I guess we will know better in a few months if this will happen or not. My focus and let's say my contribute to this experiment and to the data that we gathered and all the analysis we want to do is inferring aseismic fault slip from deformation data. So we have several types of deformation data. First of all, we have displacement measure at the injection point. So we placed two SimFIPs, and the SimFIP is a very high-tech device that allow us to both inject and measure deformation at the injection point. Deformation expressed in terms of displacement. So here I'm showing the figure and the scheme of the deformation unit of this device, which is basically made by two rings. And these two rings clamp the fault on the two different walls. And between them, we have several fiber optic cables with different orientation, and we measure strain with these fiber optic cables, which is then converted into 3D displacement. And in the case we trigger and we activate this fault, this displacement and this displacement would correspond to the slip or the tensile component on the fault. And then we also have FBG sensors, which are strain sensors. They are placed in this borel here, a monitoring borel, which runs parallel to the fault. It's almost, I think, between 15 and 20 meters from the fault zone. And then we have tilt meters placed in vertical borels that measure the horizontal tilts. And we also have DORSA, which are other 3D displacement sensors. We have two. One of them is in the tunnel and the other one is in this monitoring board here, BFE 7. Anyway, we can also, of course, measure and monitor seismicity with a dense array of geophones, acoustic emission sensors, and accelerometers. You can clearly see 2 more monitoring boreholes here used to, as I said, monitor seismicity. So the FEAR1 experiment lasted for 1 month, so 4 weeks. Actually, the true stimulations took place in 3 weeks. And at the moment, I'm focusing on some of the tests that have been performed. They were 14 in total. For each test, we had some different injection protocol. Anyway, I'm focusing on these 4 experiments, which took place in the 2nd week, but actually is the 1st week of active simulation. And I'm focusing on those because during these experiments or during these tests, we kept the pressure under the level of seismogenic pressure because we didn't want to trigger any seismicity. We just wanted to study how the fault and the experimental volume responded to hydraulic simulation. And since I am interested into looking at aseismic slip, it's easier to decouple from seismicity if you have known. So yeah, that's the reasoning. And another reason is that by looking at the strain data, so here I'm showing the traces in this 1 week simulation. So these are the 4 experiments that we did and that I pointed out in the previous slide. So looking at the data, it seemed that there was some pattern which was repeated all over the 4 different simulations. So the traces are color-coded based on the location of the sensors at depth into the monitoring borehole BFE 18. So the green sensors and traces are associated to the sensors which are deeper in the borehole, and vice versa for the yellowish brown one. And as you can see, there is a clearly transient response in the deepest part of the borehole, which is extensive, but this signal is transient. It goes down as we stop the simulation, but we see some permanent deformation, which instead is clearly seen on the shallower sensors. So that's what is driving all my analysis. I'm here showing an example of one of these tests, in particular, the one that we performed on the 27th, which we will also call test 7 from now on. And here you can see in this panel the injection protocol, so pressure and flow at the injection point together with the measured displacement in terms of opening, slip along strike and along dip of this map fault zone. You see here, this is the injection point, and these are the strain traces associated to the FPGs placed in this borehole, BFE 18. And what you can see again in the animation is clear because I'm showing the 3D and the 2D. So basically the strain pattern along the borehole is that as soon as we inject, the deepest part immediately respond, but then as soon as we stop the simulation, it somehow relaxes, but we see this residual extension in the shallower part of the borehole. And what we also see at the injection point in terms of displacement is quite interesting because we see a clear opening, which is intuitive, which is somehow mimicking the behavior of pressure. And then as we stop the injection, this opening goes down, so we have closing, but we also have a phase of slip. So this was one of the most interesting tests, but what we could see again, if we look at this pattern, is that over the test, the different tests in this week, this pattern is repeated. So here I'm comparing all the different tests, and as you can see, strain localizes with highest amplitude as soon as we go on with the test. So of course, we want to understand if we can model this pattern of deformation with a potentially triggered aseismic slip event, if the location of this patch might be on the fault zone somewhere else, and whether or not seismicity is also playing a role in redistributing the strain afterwards. So here are the results of my model with an aseismically slipping patch placed in front of the part of the bore where we measure the highest extension or deformation in general. And as you can see here, I'm comparing the observed strain in green, the predicted one. There are some similarities. We managed to well model the slope of extensional deformation, but the model would also predict some compression deeper in the borehole that actually we do not measure. But it might be that adjusting some of the source parameters like the size or the slip distribution, we could reach a better fit with the data. And in any case, this is just one scenario that we took into account. So the aseismic slip occurring on the MC fault, on the fault zone. But there is another one. So there is this coincidence where we observe the highest deformation or permanent deformation extension at the end of our simulation is also the point where geologists map several structures. So I'm talking about borehole meter 13 and 14. They observed some existent fractures which have disorientation, shown here in the stereonet. And another coincidence is that later in the experiment, so the week after when we started to inject at high pressure, we actually activated a seismicity cluster which seemed to be placed on one of these structures, and these structures are clearly, such as the seismicity, of course, are clearly intersecting this borehole. So the second scenario is that what if we activated aseismically first at the early stage of the experiment, this fault patch, which then start hosting seismicity as we increase pressure over these tests. And here the match between observed strain and predicted strain is even better. Anyway, both of the models are plausible in terms of observation and in terms of, let's say that we used just physical intuition to think about these two potential dislocation source patches. But in the end, it's clear, since both these two models predict quite well the deformation in the borehole, that it's quite a challenge to constrain the characteristics and the source parameters of this aseismic slip event that we might have triggered. So we cannot constrain with just these FPG strain data, the location, size, slip distribution, and mechanism of the aseismic slip. So it means that we need more data, and luckily we have more data because we need to add more constraints on the source characteristics. And so the next steps would be integrate this analysis with other data types, such as SimFIP and Dorsa displacement and tilt. And actually I have already started working on tilt meters data. Here I'm showing the data for the whole week and for just test 7 of the tilts that are placed on respectively on the footwall and hanging wall of the mapped fault zone. And as you can see, also the tilts respond with a transient component to the simulation, and then they remain tilted. So there is a permanent deformation that we can relate to some fault deformation somewhere. Then, of course, when we will gather all this data together, we should run a full inversion to characterize this aseismic fold deformation that we potentially triggered during the experiment. And finally, we would like to correlate the so characterized seismic slip with the observed seismicity to understand whether or not the triggered seismic slip might have promoted or prevented seismicity during the whole experiment. And yes, I just presented this update to a conference, the shuttle workshop on induced seismicity last week, and hopefully I will have more update when I will present the same thing at EGU. Yeah, thank you. Sorry, it was long.
No, don't worry, Aurora. Thanks a lot. Congratulations. Any question?
I was mainly wondering just about the size of the aseismic slip patch. We're just constraining that via the models, or at this moment you don't have other data for that, it looks like.
Yeah, sort of, in the sense that, for example, we know that there might be some slip where at the injection point. So it could be that this patch is much larger or longer, so it might be extending on the whole fault, but the distribution of the slip is different along the fault. But yes, at the moment I just use the forward models. Like I did a trial and error and see how the size of the patch might have affected the pattern of strain in this borrow. And I choose the optimal one, but I'm not saying that that's the true one.
Yeah, that's hard, I can imagine. But after you finish this work, maybe we can do some of the data assimilation that I show in the lecture after to sort of more robustly try to combine some of the word models and the data. I talked about this with Massimo Cocco already a few times, so it might be interesting.
Yes, great, for sure.
Can I add something to this?
Sure.
Just maybe Aurora, you said it earlier. I wasn't here from the beginning, but so we can only measure it in some places, but that already sort of is a very crucial point to this experiment and also to its relevance for TRED, because usually if we just monitor seismicity at the large and regional scale, then we never know about aseismic slip, and we see some, often relatively vague seismicity migration pattern, and so interpret them in terms of aseismic slip. But here we have much better observational constraints on aseismic slip, and then we can study how it relates to seismicity.
Yeah, and
that being said, it's still difficult.
Such good data, it's still hard, right?
Yeah, it's still point measurements and inferences. And so now the new experiments, we're trying to have more fault crossing boreholes so that we can measure the aseismic slip at least in multiple points. But it's challenging.
And I guess you know better now where the faults are as well, right? Or did you identify some?
Yeah. The more data you collect, the more confusing it gets. No, but we go to a different part of the fault where it's according to the ground penetrating radar images better defined.
Okay.
So because this was just a test experiment.
Yeah. Yeah, imagine. I mean, here you spend so much time and money to image these fault geometries really well, and even then it's so hard. So how are we supposed to do that in these large scale regions that we are studying? But we are learning more and more, and we keep learning, right?
Yeah.
Yes, great stuff.
Okay, thanks a lot, Aurora. And I think we can start with you, Ylona, with your lecture.
Yes. Yes, I think I will cut it a little bit short because I would normally really need to leave at 5:30 because my husband is in Munich and I need 2 locations to go to. This gets
Okay.
But I think I can relatively easily skip or shorten the last parts of that. So that is That's what we go with. But yes, good afternoon again, everybody. So essentially what I show you now in this lecture is already coming from a keynote presentation that I gave last year at the German Geophysical Union in Jena. So it has also a lot of explanations on some of the fundamental concepts on data assimilation. So I hope that that also clarifies some things for you. And then I show some results to show what we can do with that. So first of all, a big thank you to my collaborators and particularly the PhD students that worked on this. Yeah, so Hamed, you don't see my pointer, I guess. Yeah, it's always like this. Let me see if I can quickly. Yeah, I see that. I see a pointer signal, but I cannot get my mouse there. Let me see. I'm just gonna stop sharing this and see if I can get the mouse. There, yes. Now I have the mouse. I can at least annotate in Zoom. Then I share my slides. Do you see something now? Or do you only
Yes.
see when I draw? Do you see
Yes.
the mouse also?
Yes, yes.
Okay, perfect. That's much better. That will simplify life a little bit. Of course, it doesn't give control to my keyboard anymore. So now all the control is in Zoom and not in Keynote. So that means I cannot use this. I need to be able to control my Keynote. Sorry. Now at least the annotations are gone, so I will just go. We never use Zoom at the university. So now you see the slides again, I guess. Right?
Yes, we see the slides.
And I have control. So that's great. So first, a big thank you to the PhD students and postdocs, Hamed, Celine, and Duty and Meng Li that worked on most of that, of this data assimilation work in the last few years. So in the end, what we do with the data assimilation is just another interesting integration of the path that we are all following in threat, right? So because in threat, we're trying to combine the observations that we do in work package 1 with the physics information and the physics-based models that we have in work package 2 in order to forecast and assess the earthquakes and associated risk in work package 3. So what data assimilation does is just all of this in one integrated and statistically robust manner. So we haven't discussed this at any of the workshops, but I thought it would still be interesting to show what can be done, although we are very much in the early footsteps of what we can do here. But if you zoom out in general, many of the solid Earth problems that we are tackling, we have natural observations, we have laboratory experiments, and then we try to integrate these with physics-based numerical models to try to make some sense of that. So for example, like Aurora showed where the slip can be. So how do we integrate that all in a robust manner? This is very important because we have a lot of observations that are ever increasing in the types of observations that we have. Even also just looking at the FAIR experiments, there's a lot of new types of information as well. A lot more observations, much better observations. So these are critical to understand any solid Earth process, but particularly also earthquakes. And there's also been a large growth in computational power, and accordingly also with physics-based models. So we can represent the earthquake processes in a more realistic manner and include more realistic physics-based processes to really understand what is happening there. The challenge these are usually fields that go each on their own, but the real challenge, I think, is in how can we integrate these observations and the physics-based models. And there's many different ways that you can do this, right? You can do this in a manual fashion, building on your expertise or intuition, trial and error, try to see what matches, where could this slip patch be, for example. Or you can do this more in a quantitative approach using inverse modeling, such that you invert the observations to quantify what is causing that. And there's also different ways, again, to do this inversion. So you can account for observations roughly at a stationary moment in time, or very much a connected nearby in time, where you're looking at a single process and a single cause. So that's what you want to identify with this inverse modeling. Or you can do a more time-dependent version of inverse modeling, such that you try to include maybe a longer time series or more processes in this one. And if you look at fields like weather forecasting, if you have much and much more data coming in, and what you're estimating is changing as well, you want to be able to integrate that data seamlessly as it becomes available without recalculating everything. Add that data into the system all the time, and also propagate the information and the errors that are in those data, both in the physics-based models and in the observations. And that will help you to quantify changes in the variables that you're studying and changing causes and processes as well. So this is then what is done in data assimilation, which essentially is a time-dependent sort of adaptive inverse method. So if we look at the physics-based models on the left and observations at the right, what these physics-based models really do, what they're useful for, is they extend observations in space and time in the most general sense, right? Because we just, in any area of science, we cannot observe each of these things. So we need extrapolation or interpolation for which we can use physics. And then we have observations, which can help to correct these physics-based models towards the truth. They are much closer to the truth generally, although they also have a measurement error involved in there, which can and ideally should also be quantified there. So that's coming directly from, amongst others, the measurements and the equipment. And in physics-based models, we have large errors as well, either due to missing physics that we knowingly or unknowingly not solve for, that we have to discretize models. So we're making a variety of errors there. So it would be nice if we can simply account for these errors using a model errors. So in these equations, epsilon x is the model error and epsilon y is the measurement error. Did you have a question?
È caduto.
Marco, do you have a question? Or I shut off the videos, otherwise I keep looking at these moving things. But let me know if you have questions. So just feel free to interrupt if there is anything unclear. So in the end,
meglio nel...
I think Bruno, you can. Oh yeah, thanks.
Thanks. So X is essentially a whole big vector of state variables. State variables you can look at as solution variables. So these are the things that change throughout your observation window. And then you also have parameters. Parameters don't change throughout your interest period, so they are fixed. But this X is just a long vector of velocities, stresses, strain, whatever you want it to be, temperatures or pressures in the atmosphere. So when we forecast these state variables, they approximate the truth, but they have an error attached to that. And the observations are shown as Y, So if you discretize that in the numerical modeling framework at a certain measurement location that you can indicate in this measurement matrix M, you will have the truth for that point in space and in time with an error attached to it. So important to remember is that data assimilation can account for the uncertainty both in the models and in the observations, and also propagate forward those uncertainties. So this is what I said. The observations we can use to correct the physics-based model towards the truth, and the physics-based model you use to extend the observations in space and time, and try to, for example, predict forward in time, so into the future. This is where the forecasting element comes from. So in the end, these two really complement each other, and the data assimilation provides an effective way to do that integration in a statistical, robust manner. And so this is all adopted from weather forecasting. Also, oceanographers, groundwater people, reservoir flow people are adopting these data assimilation methods. It's all relating to some form of geophysical flow. So if you look at the flow of rocks on much larger time scales, you can also use data assimilation methods. So this is really, I think when I originally did these studies, 2014 or 15, when I started with that, there's very few, or was nothing that was done on this, but this is changing a bit now. But in the end, I think I started because the challenges that we have with respect to the atmosphere people or the oceanographers are very similar. We have nonlinear flow, sometimes chaotic patterns, and we cannot resolve all scales or processes that we need. While we also have very limited observations that are indirect. So like in the Bedretto lab, it's as direct as we can get essentially, but very often we are much further away at the surface. We cannot measure the fault. And these observations are very, very noisy. So we need to account for that. And they're very uncertain. For example, if you measure stress, it's highly uncertain what it is. So you need to account for these things in a single framework. So this is a figure from Hamed's PhD thesis, where in the top, you see the Lorentz models that they use in meteorology. And in the bottom, you see the Birch-Nopov models. It's like essentially the spring block models that we really like in earthquake seismology. So I will show you a little bit more, but this is just to show the similarity, right? And this is why we've been working with meteorologists also to try and make sense of measurements and the earthquake forecasting problem. So when I started with this, and I think still it's often questioned, right? Can we use data assimilation? Do we even have enough observations to do this? Well, then I thought, let's figure out how much we need. So based on the simple syntactic test that I did and that the students did, I don't think we need that much observations at all, because our medium is not changing as quickly as the atmosphere is changing. So we definitely need also much less observations. And then there's a question, are these observations that we do not too uncertain to be really useful and quantifiable? Well, because we take care of the error, this is really okay. So this is not a problem in this framework. And then you could ask also, do we even know enough about the physics? Because it's hard to know about the earthquake physics principles. And some people might argue that we definitely don't know enough. So my approach simply is to stick to the first physical principles, conservation of mass, momentum, energy. These are things that we know about physics, and we know them to be the most reliable and the best we can do. So I start with that. So now let's look at earthquake and problems here. So I will first go into a bit more on the methods of data assimilation. And then I will discuss if we can estimate stress at the fault. Can we forecast earthquakes? Yes, we can, but in synthetic models so far, it's very simplified. And then what I think I will skip mostly is about estimating the parameters in a subduction zone from observations before and after the earthquake. And then, well, in more generalizing things, what can we learn from data assimilation methods for solid earth processes? So data assimilation is essentially statistical integration of a dynamic or a physics-based model, measurements, and their uncertainties, where we want to estimate the state, so the solution variables, and or the parameters. So when I'm explaining, maybe it's useful to keep this configuration in mind. So here we're just looking at a simplified subduction zone from a laboratory model, where the tilting surface is the Earth's surface, and horizontally we see the megathrust of the subduction zone, and below is the plate that is subducting down, that is not modeled. So in much of what I showed at the beginning, we just look at one data point at the surface near the coastline, and then we analyze what we do at one point in the middle of the fault. So, and you can look at the surface velocities, for example, and then the velocities at the fault or the stresses at the fault. So let's look at this single point at the surface here. So the general idea is that if you come at a time step where you have a certain observation y, you can forward propagate your numerical model up to that time, but you're not doing that with one model. You're doing that with many models. So you're generating an ensemble of models that together gives you this prior probability density function in blue. And what you have at the same time is the observations y and a measurement error around that that indicates the width of this, the likelihood or the probability density function here. So it's essentially data assimilation is a recursive Bayesian estimation method. So we use Bayes theory here. So you calculate the posterior probability, shown in green, of the state x, given a certain observation y. And that is equal to the prior probability that you had from the numerical model in blue, so px, multiplied with the likelihood of an observation y, given a fixed model x. So that is your red probability density function. And you divide that by the marginal probability of the observation, which is essentially to normalize the values that you're dealing with. So there's many data assimilation methods, because obviously weather forecasting is a very well developed field. So broadly you have sequential or direct methods. These are ensemble common filters and others. And you have variational or iterative method. These iteratively solve a cost function, but in the end some parts are quite identical. And it just depends on what type of forward problem or model or physical problem that you have. Essentially how nonlinear it is, what scales that you're looking at. So if you're interested in that, check out this reference that gives a nice overview for weather forecasting models. You can also make a hybrid version between these sequential and variational functions. So what we do is we just start with sequential methods, because essentially our forward model has a discontinuity that represents the brittle failure in form of plasticity. So it becomes quite hard to build the adjoints and things. So we just use the forward model itself that already knows how to deal with that, to simulate that forward without accounting for that in the iterative procedures. Moreover, these ensemble common filter methods tend to work really well already. Mathematicians can't really explain why so well, but since it's the simplest that meets what we know, this is what we start with. So if you look at ensemble-based data assimilation methods, what we do in order to account for the nonlinear dynamics in the system is essentially use a Monte Carlo type of approach, in which we have many randomly generated ensemble members that we're propagating forward in time. So we just have many different forward models that we are propagating in time, and then we don't need to worry about solving the nonlinear physics, because that's what the forward model that we already have will do. So essentially, if you look at this figure with the x-axis in time and some state variable can be anything you want. You see the model line in green, where at certain times where we have the observations, you're making a forecast based on your model of what this variable, for example, imagine what the velocity at the fault would be. Now, if you're adding data observations at a certain point tk, where you have the truth here, you want to update your model with that. So there's different ways to do this analysis or to do this update. So what we use, as I said, is this ensemble common filter, but there's also a particle filter. That's also a common method that I will explain a little bit later because we use it there as well. But these are very similar methods for you, just they're filtering methods. That's fine. And these methods can take care of high-dimensional systems fairly well. And the ensemble common filter is just the simplest one, the most efficient one. That's why we start with that. So as you move through time, if you have your posterior probability function in red, now I need my mouse, but sorry, I just explained with words. After you added that observation, you just propagate forward your many forward models again, following the green line, until you have a new observation again, where you can add that, do the analysis that you have, and you get a new posterior probability density function. Once you've corrected all the model, each of the models, you go again and propagate forward in time again until you reach tk plus 2, where you have another observation. So hopefully in time you're getting closer and closer through to the truth, also with your forward model, such that you can then forecast again to go to the next point in time where you have data. So this ensemble common filter is essentially a least square minimization of the misfunction j that I show here. So essentially this weighs both the distance to the model and it weighs the distance to the data, both depending on the error that you have there. So you have the data likelihood and the model prior. So if you write that in sort of the classical ensemble common equation, remember that the x's were all these long vectors, but it doesn't matter to understand the equation. You can also just imagine one number, one velocity. At one point, you can calculate the posterior probability density function based on your, let's say, 150 models or thousands of models, starting from the prior, x and f. So this is your forecast from the numerical model, plus the covariance matrix multiplied by a data error and a model error component in light gray. And this is then multiplied by the data misfit. So how the model, I really want an arrow here. But anyway, sorry. So how you're going to update your prior in green depends on the data misfit, and how to change the data is stored in the covariance matrix. The covariance matrix is here green because that information is also given by the physics-based forward models, the ensemble of that. Because these forward models know how the velocity at the Earth's surface relates to the velocity at the fault and the stress at the fault. So this covariance matrix is just a very big matrix connecting each of the points in the model. So if we need to change the velocity at the surface to make it faster, the covariance matrix can tell you how much and how to change that also at the fault, while you're also accounting for the data and the model error. So if either of these is very large, the update will not be very much. And then, so in your prior is every expert knowledge and every piece of lab measurement and everything you know before. But in the next steps, when you get new data, that prior also contains your previous observations. And you can just go through this update process step by step. So now if we go to earthquakes, can we estimate fault stresses? And and do some very, very basic earthquake forecasting, go in that direction. So you know from the meeting in Dinther that we did that stress is very important and strength is equally important. If the stress reaches the strength, an earthquake can occur. So that also means what you really would like to know on the fault in an ideal world would be to know the stress and the strength and the evolution thereof. Now, this was anyway also when I started with this, but even now that we have the fear experiments, it's still very hard and impossible essentially to know the stresses and the strengths at the fault. But that would be an ideal world. So we check with synthetic models. If we have that, what can we do and what would we need? So as I said, the fault is inaccessible. It's too far and observations are very few. So up to now with other earthquake forecasting, we really rely on many of the other statistical methods that have no or limited physics in there. So you have seen many other presentations of that, and you will see in a workshop that is coming up very soon. So what we do in terms of the physics-based simulation is just, these are dynamic forward models, solving the conservation of, well, depends on which one of I show, but it's essentially the conservation of momentum and mass that is most relevant, different constitutive equations, so different rheologies, can be either fully elastic or viscoelastoplastic, and different frictional formulations, either rate and state friction or a simplification thereof. So we've discussed that endlessly, so I won't go too much further in that here. So this is the first perfect model test that I did when I was still at ETH, working with Andreas Fichtner and a mathematician that is in the math department there. So we just wanted to know what is, can we estimate the rate of stress at the fault at depth? So this is the figure you saw in the beginning. We're going to look at the purple dot that is in the middle of the fault zone. And at the yellow dot, we add the data near the surface where we extract from the numerical model. So it is a synthetic test, a perfect model test. We extract the velocities and the stresses of the true model. And then we add errors on top of that we scale from natural observations. That means that the stress error is gigantic, larger than the stress drops and anything you have, but it's gigantic. Let's see what we can do with that in this synthetic case of a subduction zone. So we are forward propagating 150 ensemble members. So on the top left, you see one example of an outlier ensemble member. So the velocity that we observe there at the surface is not close to the true model that is at the bottom left, where you see that the true model is just before a large earthquake, with stresses are very high. Well, in one of these ensemble members, there was already an earthquake before, so stresses are very low. If we do the Ensemble-Kalman filter and we do one analysis step, adding only one observation at the yellow point in time, the physics-based model can reconstruct this stress pattern, as you see in the middle in the analysis, fairly well, because it knows from 150 other models, if you have such and such velocity, what would the velocity and stress pattern at the fault look like? And so if we try to understand that in a bit more deeply, let us look at just two parameters. So on the x-axis, the horizontal surface velocity, and on the y-axis, the shear stress at the fault. And we're just going to assimilate one piece of data, and that is the horizontal velocity at the surface. No other data, because then we can actually follow step by step this Ensemble-Kalman filter equation that I put at the top. So if we look at the first term, that was the prior base forecasted based on the physics-based model. So we've let each of these models run for quite a while and have some events such that each of these models don't know anymore what the state of stress at the fault is. So you then see the probability density function at the right for the shear stress, for example. This is all over the place. The truth is in the black dashed line, and the mean of those 150 ensemble members is in the green dashed line. But we essentially have many, many models there. So we don't know what it is. So if we then look, for example, at this magenta model, it's a single model. If we look on, that's completely on the left. So there's a very large data misfit here. So this term in the middle with the covariance matrix tells you how to update each of these models. So if you assume a single data point, that is still fairly easily doable because the covariance matrix is also fairly simple to calculate, and it's essentially just your least square fit of all these 150 models that you see. If you do a least square fit, you get that black line, which in this simple configuration is your covariance matrix, or tells you from the covariance matrix multiplied by the measurement matrix transpose how to update that purple model. And so that line, that slope, we get from the physics and all the other models that we know. So if we now want to update this single model and say, no, the surface velocities that we observe there, they don't relate to what is in the true model. So update to near the true velocity, not exactly because there's a measurement error there. So there's still an error that we account for there. So the stress should be higher than it was because the event didn't happen yet on that model. So you make a higher stress following the slope of the covariance matrix here. So if you do that, you generate the blue model. That is the posterior probability density function that you see on the right there. So overall, for many of these models, the stresses are increased quite a bit, and the mean of that in dashed blue line is also increased a bit there in this one step with 1 point in data that we add. So we didn't do any stress measurement at all. We didn't add any stress measurement, and still we can update the shear stress because the model knows the physical connections between the two. Now we have, from the borehole that we tried to mimic in this synthetic test, we also have the vertical velocities, and we have 3 stress components that have a very large error attached to that. So if you add that information, the slope across which you update the shear stress changes to account for each of these pieces of information. So based on those observations, it knows that the shear stress should be increased, but not as much that were based on only the horizontal velocity. And so you're approaching the true stress that you estimate at the fault a little more. And we can do that over many, many steps in time that are shown on the left graph with each of the gray lines. So essentially, what is it? 10, 15 times in an interseismic period, we're adding information into the model from that point at the surface. If you look at what we then think the horizontal velocity at the fault should be in the top figure, you see the true solution in black again. You see the mean of the ensemble in red, a box around that with the standard deviation, that's in the top figure, not always clear, and then the minimum and the maximum models that are also shown there for each of these 150 models. So you start data assimilation at the blue line. Prior to data assimilation, the mean in red doesn't know when the horizontal velocities increase. Can be at any of these times. But as soon as we start to assimilate a little bit of data, the first event even occurs after we've assimilated 2 or 3 data points. The mean already starts to show that it expected an event there as well. But interestingly, after that event, all the models, all 150 models predict there will be no earthquake. until we start to approach the next event that we have here. And then after that event is still the same. So you see in general, in very many interseismic periods, at least all the 150 ensemble members say that not to expect an event up to the end of the interseismic period, where more and more models start to show that you would expect an event. And this works for the velocity because the model have an idea on the shear stresses. So the shear stress is the figure below that. So before the data assimilation, the shear stress is not known, but the minimum and maximum of the stresses are known because it's a synthetic test, so we know the parameters. So once you start to assimilate data, the model knows here, well, I had to increase the shear stresses, and after the event was there, it knows the stresses are dropped. And as you keep propagating forward in time, and you see that it can capture this shear stress pattern fairly well once we add the data into this simple perfect model test. So even also if we have stress measurement with large errors, this is very useful. I don't show that all here, but you can assume that it helps. Not the only critical thing though. So if we look at the forecasting, we saw in this figure, you see some very large events that are not fully periodic, but quasi-periodic. So if you use a periodic model to try to forecast that, I show the results in this red dotted line. So what you see is an error diagram, where on the bottom axis is the duration that you sound an alarm. So on the left, 0, you sound an alarm for 0% of the time. And on the right, on the 1, you sound an alarm for 100% of the time. Then on the y-axis is your failure to predict an earthquake. So at the bottom is 0, means you predict all events that are in this synthetic lab sequence. You all predict them wrong. If you all predict wrong, you're at the top with 1. So you fail to predict everything. If you fail to predict 0, so you correctly predict everything, you're at the bottom again. So the left corner is your ideal goal where you would want to be. Now, every earthquake scientist will know that that is totally and utterly never able. And many earthquake forecasting ones are around like the random line, or the very best ones go a bit beneath that random line, but it's very, very hard. So this is what politicians would like to see, but it's not really what we can give. So I tested this for the periodic model that is in the red dots. Because the sequence is quasi-periodic and not periodic, that doesn't do very well, so it doesn't really help us. The line for the data assimilation is shown in red here. So you can look at different sizes of events. In this case, I look really at the large events only. So here you see from the graph that the largest 4 events could be forecasted if you sound an alarm 17% of the time. So this is for any like earthquake forecast, this is great. For politicians, it's absolutely not good enough. So, but we're taking step by steps. We're doing something very simple in synthetic numerical models. So can we also do this for nature? We wanted to test that on laboratory experiments, and this configuration of a very large fault in Japan that is studied by Yantao Yi and André Niemeyer a while ago. And we built a numerical model configuration to test this. But also there, Ahmed, when he studied his PhD, had to start simple, just from synthetic tests to even understand more. Because my previous model did laboratory experiments, and the laboratory was made of gelatin, which has slightly slower accelerations than real seismic slip rates. So since seismic slip rates are really much faster, we didn't know yet if earthquake, the forecasting that I showed would work also for really seismic events or only for slowers. So that's when we built this 1D model of the laboratory. We use rate and state friction, we resolve everything in time, and use an Ensemble-Kalman filter again. So can we also estimate the fault stress at seismic slip rates? In this figure, you see that we can. So before the orange line, there is no data assimilation. So shear stress, the mean in green, doesn't know when there will be an earthquake or not. We still know the range of the stresses because it's still a perfect model test. So we know the parameters that we put in. And then once we start to assimilate data, you see that the shear stress pattern, the evolution is captured really well also for these seismic slip rates. So Hamed showed us we can do this both for earthquakes in terms of estimating the stress and the velocities at the fault based on the observations that we add that are in green. In red, sorry, for colorblind people, it's not very useful. So you have the observations there in the dots in red. So it's not that much observations that we add. And then the physics-based model can itself interpolate a lot already. So the same, we can also do that for slow slip events, which might be in terms of in practice, in nature, since we have many more recurring slow slip events, this might be a much more useful application at the short term and to test if this really would work in nature. So we have the same error diagram that I just explained. So also here in the case of seismic slip rates, it goes very well for these large events. Now, still, that sequence that you saw here is quite quasi-periodic, or even much more quasi-periodic than what I had. It's fully periodic. No, let's say periodic. So what happens if we make that less periodic? That's what you see in green. So you see on the x-axis that the root mean square error increases quite a bit if these sequences become aperiodic. Aperiodic is, of course, what earthquakes in nature are. So we need to work a little bit further on these data assimilation methods. So we work together with some of the best people in weather forecasting using this 1D Birch-Knopf model. So this is just your spring block model where you have many blocks connected via a spring. And then you're driving that plate, and the surface in between the blocks and the bottom is governed by rate and state friction. Why do we need, how can we improve these data assimilation methods? The Ensemble-Kalman filter assumes Gaussianity. So Gaussian priors and Gaussian measurement errors. A Gaussian prior is fine on the left red part where you are in between earthquakes in the interseismic. If you look at all the models, a Gaussian distribution is not so bad. If you look just before the earthquake, some models have shown already an earthquake, some models not. So this distribution is no longer Gaussian. It's a bimodal distribution. So that's where the weather forecasting people got really enthusiastic, and we can improve, we can do some things. It's more nonlinear, it's more non-Gaussian, that's great. So one of the things that they suggested to use was this particle filter methods. In the interest of time, I won't go in it too much, but just know that you don't assume a Gaussian prior anymore. So your updates can flow and can be curved as well. And then there is a new filter that's called adaptive Gaussian mixture filter. That's essentially a hybrid between the Ensemble-Kalman filter and the particle filter. So if you look now at this series, that is much more aperiodic. You have smaller events, larger events. So it looks something more realistic than what we would expect from earthquakes. You see that each of these models, particularly the blue and the red one, so the Ensemble-Kalman filter and the adaptive Gaussian mixture filter, still approximate the truth in black quite well. The particle filter has a much larger distribution, has a much more uncertainty in it as well. So there is less certainty about knowing where an event will come, but it has a wider breadth, essentially, of the models. So this is maybe too complicated to explain here, but you see that both this Ensemble-Kalman filter and the adaptive Gaussian mixture filters are already very close to the true solution, but in nature will not be close to the true solution. So you probably need a bit of this dispersion or a bit of the larger breadth from the particle model. So I think these Ensemble-Kalman filter and the particle and the mixture will work really well on this set, but as soon as you get data that is far out of your model, it's much harder to incorporate that, and that's where the particle filter might help. So essentially for nature's unexpected complexity. Yes, so what helped also in getting the good solutions here was using a stochastic model error that essentially represents the missing physics. We're missing a lot of physics if we just do rate and state friction in a quasi-dynamic model, I think here, for example, of wave propagation, but of other scales that we cannot resolve as well. But we can include that very efficiently through the model error to ensure that this works still quite well. So everything you saw up to now was simply that we knew the parameters. So we know the friction, you have an idea then, if you know the normal stress, you know the total strength. But of course, in nature, we don't know many parameters, for example, the friction parameters. So if we don't know them, they're biased. So Arundhati Banerjee did a study on that. So what if these friction parameters are biased? Can we estimate these friction parameters along with estimating the stress? So she found that if you have a well-known parameter for the friction, so in ideal cases that we see in laboratory experiments, the state estimation can accommodate this bias through a variety of tricks. So this is even the state estimation just itself, just from the errors that we have in the system on the model error and the measurement error. So you see that the red line with the posterior mean follows the truth in black fairly well. You see where we put observations there. Now, if we don't know this friction very well, obviously it becomes much harder to then know when these events would occur. So it's the observations from the true model that will still know that and correct the posterior back. So if it's poorly known, you'll see that the performance, the red line, becomes much worse. So sometimes it misses events, sometimes it does it right. But the state estimation, this is just pure from just the model error. You can do some tricks that they have in weather forecasting, also make this model error a bit larger. And then if it is poorly known, it's doing quite okay in correcting the periodicity and the timing of these events. But the best way is to add also the friction parameters in the state vector and estimate that at the same time. So that means doing a state and parameter estimation. If you estimate both friction and the stresses at the same time, then you see that you can recover this recurrence and when these earthquakes will occur again. So that's really quite nice, because I originally expected that estimating both friction and stress at the same time from very limited observations would be incredibly hard and probably not possible. But if we look in these first two events, and you can look a little bit more in detail, that in the top you see the state diagram, so with the stresses and the state, and in the bottom you see the friction parameter, where the black line is the true friction parameter and the red gives you the posterior So even at the first earthquake here, you can start to estimate that friction parameter a bit. And if you look at the second one, that fit for estimating the friction parameter is improved quite a bit. So you can separate both stress and friction, which is very good news, I would say. But still, this is all synthetic. So our aim was really to do this also in the lab, where we have a lot of observations, but not exact parameters or exact control on other things, and missing physics as well. So in this configuration, we also have different sizes of events. We have a bit of an idea on the initial pressure on the fault. So we use forward models to look at this. So right now, we have the forward modeling working and tuned, but unfortunately, Hamed finished his PhD without being able to finalize this and to really get this data assimilation to work on the lab experiment. So it's just simple technical things that are stopping us, but this time was over. So if you have other people that are interested to continue this, just please contact me. So this is the part that I'm gonna skip now in the interest of time. So essentially, we just use observations before the Tohoku earthquake and after the Tohoku earthquake. So both integrated in a single framework to see if we can match both types of surface velocities at the same time. So this is the work that Celine Maasman did. So we have another more kinematically constrained earthquake sequence model, and we estimate the power law parameters for the viscosity. So you see that we can estimate some of these things, say things about viscoelastic relaxation and afterslip, that we can separate them out. That has implications for the viscosity as well there. So that would, the whole story is for another time, but essentially what this shows, you can also go zoom more in time just before and after earthquakes using this data assimilation approach to estimate parameters. So if you zoom out a little bit more, just thinking about what we learned from using sequential ensemble-based data assimilation for solid earth processes, what I think now is that even if we have few measurements with large errors, that is useful as well. And there's definitely potential in using that. Of course, nature is a lot harder. I mentioned that quite a few times, but it's a very good method to deal with the challenges that we are dealing with on a daily basis as well. And since the changes in solid earth processes are slower, we also need much less observations. And there are rules of thumbs available to analyze this feasibility and how much you could need as well. And these ensembles of physical models they contain a lot of information as well. So one of my colleagues, she just published this book together with the other collaborators as well. And there's more books available on data assimilation now in earth sciences. So if you want to read up, there's definitely points there. You can also start from my 2019 paper, where I try to explain all of this for an earthquake science audience. But the best thing that I used was this book of Evanson 2009 that was just on ensemble Kalman filter. So that is the best book to start with if you want to really learn more from this. And then in an outlook, also AI will help a lot, right? That's what we're already seeing in weather forecasting. Much of the processes that are below the scales that we can resolve, those are opportunities for AI to replace pieces of the puzzle. So in the end, I think data assimilation is really important because it allows us to incorporate the physics in a consistent manner, but still we can use machine learning to make adaptations there and add things in there. So I think combining these two is where eventually in your futures, when you are much older, things might be going there. So in conclusion, I think we can estimate the stress and velocities at the fault Also parameters is what I showed you. We can do that for seismic slip, aseismic slip. Also if Gaussians are, if priors are non-Gaussian. Also because we can incorporate uncertainties in the model error really nicely. But, big but, all of these things were done synthetically in models where we know the physics and we know the parameters. So this really needs evaluation first in the laboratory, either in the models that we had or in the Barreto lab, before we can even move towards natural observations. But we can do natural observations if we just focus on a simple part of the earthquake and not use it for forecasting, but use it for different ways of combining observations and physics in the inverse modeling framework. So even though we have few observations and large errors, I think it's still useful and holds promise. So just one announcement also for you, because I received this ERC Consolidator grant and another project that gives me together like 3 million euros to look at an integrated form of this earthquake system. So both in terms of the physics that we already explained and discussed a bit in Dinther, where you have plate tectonics, the fault and the mantle, that together are needed to also understand the vertical velocities that we measure. And by adding the data of the vertical velocities, we can infer processes and future earthquake locations significantly better. And if we also integrate that system through time, before, during, and after earthquake, we create one big system where we can use a lot more data and more physics to understand earthquakes. So that is, if you know any interested potential PhD students or postdocs, please drop me an email. I can forward them the advertisement that's coming out this week, or I can just forward my email also to everybody, and then I would be very happy if you can inform the people that you know. So thank you very much. Even with that, it's still a little bit late on time, but I hope you understand a bit of what I have been trying to tell you here about data assimilation. So any question, just anything, just say so.
Yes, Ylona, thank you for the lovely lecture. One of the things please tell me if I understand it correctly or not, the quality of this iterative process depends much on the quality of your covariance matrix.
Yes.
So I see as this also an iteration that improves this covariance matrix over time. Or are we just supposed to understand what's in there from the physical parameters that we've measured in the field or something?
This is when I started with this. I wanted to understand this covariance matrix, right? Because this is what tells you how to update. So that's why I showed the different figures on how to do that if we have the data. So it is possible to just plot and study the different elements in the covariance matrix. So I did that now for 1 and 5 observations, but things get much more complicated if you do many more complicated things in the model, and then at some point you will lose the understanding of that.
So do you then also, with losing understanding, also lose trust about its correctness?
Yeah, so what we put in is we try to do the best physics that we can, right? And then correct that with the observations. That's, I think, the best we can do.
I mean, the
and
results
we know we make
astounding.
errors, right? That's why we still account for this model error. So if the model, for example, gives velocities can be anything, okay, it will ignore the model, because obviously the model doesn't know. If there's quite an agreement in the model, within the models, like, okay, maybe there is more weight on this, and it puts more weight on that correction.
Okay. Thank you.
Welcome. Aurora? Aurora?
You are muted, Aurora.
Sorry. So my question is, what would be the role of the dimensionality of the model into this process? Like, because I think that the more parameters we have in our model, the the more uncertainties we have, because each parameter is associated to a range of possible variations. So I was wondering what happens then to the forecasting, to the predictions, if we keep adding complexities to the model.
Yeah, so you have this nice weather forecasting diagram that I showed, where obviously they also have very complex models and very simple models. So part of the methods that they've developed are designed for this high dimensionality, large non-linearity. So it goes much better than I expected, but still simpler is better, right? So if we need to step from this more simple synthetic case, we really need to go step by step to trace that to larger ones. So yeah, so there are different methods out there depending on what scale and how chaotic you can choose, but I think the Ensemble-Kalman filter is a good place to start always. And also, if like I would do that in the Bedretto lab, I think you're just starting with that, and all the parameters and information that you have with that might get you actually already somewhere. But then you will have a lot more data that you don't understand. So the question is, does the model understand that? If we cannot understand, yes. I don't know.
Yeah, the thing is that we might not have the knowledge of the physics, and that's what makes the data not interpretable.
Yes.
So it's a mess.
Yes, exactly. So with including this model error, at least if the model shows, look, we don't know anything about this, it will just put a low weight on that. So it's a nice way to already account for that. And maybe in some events you will have some more better information, and then that can be used.
Right. Thanks.
Welcome. So are there other questions? I hope that people could still follow a bit of this. Oh shit, did we do a recording? Yes, right? Yes. Sorry. So now,
I think we did.
now that is also under recording. But I think I heard it start.
Yeah, Bruno is recording, but he's blocked. His computer is completely blocked.
Oh.
So he cannot turn on neither the video nor the audio. So
Okay. Well, good that there is a recording, then other people can listen to it as well. So also, if you have other questions that are simpler, let me know, right? Or if you want to think about things, discuss at later points, that's all fine as well. Yes?
okay. So Bruno charged me to say thank you very much, Ylona.
Welcome.
For a very interesting lecture, challenging. And so if there are no other questions, he also asked me to turn it off.
Okay, have a good evening, everyone.
Okay.
Thank you very much, Ylona.
Thank you.
Bye.
Goodbye.
Thank you.
Bye. Thank
Bye-bye,
you,
everyone.
everybody. Bye.